Imagine a sophisticated large language model flawlessly reciting turn-by-turn driving directions through the dense, highly structured grid of Manhattan. It tells you exactly where to turn, which avenues to cross, and how to navigate the traffic patterns with perfect linguistic accuracy. But then, researchers introduce a tiny, almost imperceptible physical deviation to the environment. They randomly block just 1% of the streets on the grid. Confronted with this minor roadblock, the AI's navigation performance immediately craters. It cannot calculate a viable detour, and the system fails entirely. This animation illustrates exactly why that failure happens. Autoregressive language models operate by predicting sequences of textual patterns based on statistical probability. They are floating completely disconnected from the actual 3D structural street grid beneath them, lacking any coherent internal map of spatial reality. When a system collapses from a single minor detour, it exposes the limit of linguistic fluency. Sequence prediction can generate a convincing description of a path, but it lacks the internal map required to navigate the actual territory. The blueprint for solving this limitation actually dates back to 1943, proposed by a Scottish psychologist named Kenneth Craik. Craik studied biological cognition and hypothesized that surviving organisms don't simply react to stimuli. Instead, he argued that human neural architecture maintains a small-scale model of external reality continuously running in the background. This internal simulation is a survival mechanism. It allows us to test out physical alternatives, calculate the consequences of our actions, and essentially let our bad ideas die in our own thoughts so that we don't have to die in the physical world. To replicate this biological necessity, artificial intelligence must evolve into what researchers call world models. As this visual transition shows, it requires abandoning linear strings of text and compressing data into a latent state space, a multidimensional environment where physical entities and causal rules interact. Building these models moves AI beyond pattern matching, allowing an agent to operate based on the causal rules of its environment rather than the statistical likelihood of its training data. While the necessity of world models is widely accepted, a fierce philosophical debate is dividing the AI industry over exactly how these internal physics engines should be constructed. One approach is the generative simulator, championed by systems like OpenAI's Sora. This method attempts to understand the physical world by generating highly realistic, high-fidelity future video frames based on prompts. This approach requires massive computational power. As we can see in this 3D rendering, the system bogs down trying to predict irrelevant, high-frequency noise. It expends raw mathematical capacity calculating the exact pixel position of every blade of grass moving in the wind, which has zero bearing on how an agent actually navigates a space. In direct opposition is the Joint Embedding Predictive Architecture, or JEPA, theorized by Meta's chief AI scientist Yann LeCun. Instead of trying to render a visually perfect scene, the JEPA framework entirely discards raw sensory pixels. It forces the system to predict the abstract, semantic consequence of an action, focusing exclusively on the causal logic of what happens next. Will a heavy object break a glass table? You don't need a perfectly rendered 4K video to know the answer. Sacrificing visual aesthetics to prioritize strict, high-speed causal logic separates a media creation tool from a functional robotic brain. But even with efficient architecture, every world modeling system faces a fatal mathematical vulnerability known as rollout drift. Drift is a byproduct of the closed-loop autoregressive mechanism you see here. An AI predicts a future state, and that newly predicted state is fed directly back into itself as the verified ground truth for the next prediction step. It relies on the exact same physics as a golf swing. If the club face is off by just a fraction of a single millimeter at impact, that microscopic deviation expands exponentially over distance, causing the ball to miss the target by 50 yards downrange. Because no neural network is perfectly accurate, a seemingly excellent error rate of just 0.5% per step recursively compounds. After just a few hundred simulation frames, the AI's imagined future completely decouples from the constraints of physical reality. Evaluating an AI model purely on its single-step prediction accuracy masks this fatal flaw. If an autonomous agent acts on a drifted, hallucinated simulation, it will inevitably execute dangerous and irrational behaviors in the real world. To neutralize this compounding math, engineers have developed an advanced countermeasure: hierarchical latent world models,
frequently referred to as jumpy models. By separating the timeline into distinct layers, the system intentionally stops trying to simulate every single micromovement. It completely abandons the calculation of millions of high-frequency primitive motor commands. This animation illustrates the benefit.
The high-level world model skips the noise, operating over long time horizons to predict the macro outcome of an entire extended skill. It visualizes the consequence of navigating to the target door, cleanly bypassing the microscopic physics of individual walking steps. Predicting these extended skills drastically shrinks the combinatorial search space. With fewer steps to calculate, there are fewer opportunities for mathematical errors to accumulate. By utilizing hierarchical abstraction, a machine can maintain a deep, stable semantic plan without drowning in the mathematical static of physical execution. The final layer of this evolution involves advanced classical physics, specifically the integration of Hamiltonian mechanics into AI architecture. Instead of hoping a neural network slowly learns the rules of nature through trial and error, a Hamiltonian system explicitly hard codes laws like the conservation of energy and momentum directly into the AI's latent space. This mathematically prevents the system from generating physically impossible hallucinations. When the AI dreams up a future sequence of events, those events must strictly obey the structural realities of the physical world. Integrating the linguistic breadth of language models with the physical constraints of world models creates a dual-process system. It allows a machine to verify its vast informational database against the grounded, stateful logic of its internal physics engine, testing the viability of an action within a simulation before executing it in the real world.